So in this video, we'll continue with exercise 721. So we're trying to draw the complete SN1 mechanism for a few reactions. And there's one typo here. There should be an iodine on this carbon. And I think in your homework, if there's not an iodine there, you want to be sure to draw one there. Okay, so once you have once you have the correct exercise written down, we're going to follow the same steps we went through before. We want to think first about which of these steps in the possibilities, which of the possible steps in an SN1 reaction are we going to have in this specific reaction? And the first one, to know whether we have this proton transfer, we would look at the leaving group. So here that's going to be the iodine. Iodine is an amazing leaving group. It is so big. It's not only a halogen, it is the biggest of the halogens. It is gigantic. So it can take a negative charge and spread it out over its whole area, make it really dilute, and be really stable with it. So it's an awesome leaving group. We definitely don't have a bad leaving group, so we don't have to do a proton transfer to make that iodine a better leaving group. You always have to do loss of a leaving group. That's just part of a substitution reaction. Let's think about the possible carbocation intermediates. So when you're thinking about that, cover the leaving group up with its electrons and replace it with a carbocation. Because when the leaving group leaves, it leaves behind a positive charge. Now that carbocation is secondary. It's bonded to 2 other carbons. If you compare it with the carbon below it, that would be primary, so that would be a less stable place to have the carbocation. But if you were to look to the left, that is more substituted. There's no hydrogen there, but if you had a methyl shift, then the carbocation that would form there would be tertiary. So that's a more stable carbocation. So we will have a carbocation rearrangement because there's a more stable place adjacent to the carbocation than where the carbocation is. Okay, nucleophilic attack you always have. It's bread and butter of a substitution reaction. And then proton transfer, we'll only have the proton transfer at the end if the nucleophile has no full charge. This ET here is standing for an ethyl group, so CH3CH2 and then OH. So that's ethanol. ETOH is drinking alcohol. Notice that this is completely covalent. There's no full charge there, no full negative charge. And if the nucleophile has no full negative charge, you will have a proton transfer at the end of the reaction. So these are the steps we have to consider. Our first step is loss of a leaving group. So we'll draw our molecule. And we're going to show loss of a leaving group in that. Iodine's leaving group, it can take its electrons and pop off the molecule. So that would leave us with the structure. The next step that we realized we were going to need to do is the carbocation rearrangement. So that's what we're going to show here. This carbocation currently is secondary. Carbon it's bonded to is bonded to 2 other carbons. But what you can do is you can take one of the methyl groups next door and move them over. So that's the carbocation rearrangement there. That's the mechanism for that. It's called a methyl shift. And when you do that, you now have 1 methyl group left there. This other methyl group has gone to the other carbon. And now the carbon missing electrons is that top one. So the carbocation has moved over. So the carbon skeleton really changed because of that carbocation rearrangement. The next step is nucleophilic attack. So we have our good electrophile here with our full positive charge. Our nucleophile, the nucleophile they give us is ethanol, ETOH. So that's this ethyl group this ethyl group, CH3CH2, with an OH at the end. Now on that, you have that oxygen, which is really electronegative. Let me just expand this a little bit. There's a bond there between the oxygen and the hydrogen. So that oxygen is really electronegative, and so it's slightly negative, and the carbon is slightly positive, and the hydrogen is slightly positive. So the oxygen with the slight negative charge in the lone pairs is our nucleophile, and that nucleophile attacks the full positive carbon in the electrophile. And so that would give us we still have the methyl group there. Now we're going to have this oxygen. The oxygen is bonded to a hydrogen and an ethyl group. It had 2 lone pairs, now it has 1, and that gives it a full positive charge. So this isn't going to be our final product because this is still kind of unstable. So we need to make that more stable by doing a proton transfer. And that was the last step that we had here. So we'll have our proton transfer. And so we just need some sort of a base, and they don't give us too much here. We have the iodine. We could maybe use another ethanol molecule. Let's say we use the iodine. After the iodine pops off, it's running around. It has a full negative charge. It could come back. Probably it would be an ethanol molecule that would do this instead, but here, this full negative charge can steal that hydrogen. The electrons can go on to the oxygen to stabilize the positive charge there. And so you end up with that, which is our product. Now in what they drew, instead of this top part being a carbon chain, they're going to write ET, but remember the ET is just standing for that ethyl group. So this is really the same as this. And so that's the mechanism for this. We had loss of a leaving group, carbocation rearrangement, nucleophilic attack, and proton transfer. Okay, with the process is going to be similar. First, let's see which steps we're going to need to do. So first, look at the leaving group. Is it good or bad? OH is a terrible leaving group, because if it tried to come off of the molecule, you would have OH with a negative charge. Oxygen's a pretty small atom, and so it's not able to stabilize that negative charge very well. And so this is not a good leaving group. We have a bad leaving group, which means that we have to do a proton transfer in the beginning in order to turn that OH into a better leaving group. We always have loss of a leaving group. Let's think about carbocation rearrangement. When you're trying to think about carbocation rearrangement, erase the leaving group and picture a carbocation in its place. Now that is a tertiary carbocation. Next door it would be primary, primary, or tertiary. Nothing next door is more stable than that carbocation, and so it will not rearrange. So we won't get carbocation rearrangement here. We always get nucleophilic attack, otherwise we wouldn't have a substitution reaction. And then here, if you want to see whether we have the proton transfer at the end, you have to look at the nucleophile. Now, there are 2 things here, and at first blush you might think that either of those could be the nucleophile, but look at what adds on to the carbon chain. It's the OMe. So this MEOH is our nucleophile. Now, Me is standing for a methyl group, so that's really CH3OH. So that's a methyl group, and you'll notice that here, that is a completely covalent compound. You have no metals there. So there's no full negative charge there. And if you have no full negative charge on the nucleophile, then you'll have to do a proton transfer after it attacks. Okay, so those are our steps. This is our plan. Let's hop to it. We have our molecule, and we need to turn that OH into a better leaving group. So the first step is this proton transfer, to turn that into a better leaving group. So you can mix this with a couple things. I think the most straightforward thing, though, is to mix it with sulfuric acid. Now, sulfuric acid looks like this. It's a good structure to know. It'll come back in organic chemistry, too. You'll want to be able to draw it then. It looks like this. You could see why it's such a strong acid, because if a hydrogen tries to leave without its electrons, so H plus donor, that's what an acid is, then you have that lone pair left on the oxygen, and that is allylic to 2 pi bonds. So it's spread out through resonance over a lot of the molecule. And so it's able to really stabilize that negative charge, that lone pair. So that's why sulfuric acid is such a good acid, and hopefully that explanation will help you to remember the structure of sulfuric acid. You might also be wondering why sulfur here has so many electrons around it, right? It has 2, 4, 6, 8, 10, 12 electrons around it. And that's because sulfur is pretty low on the periodic table, and so it has d orbitals that it can fit electrons into. Remember, the reason for the octet rule is you have an s orbital and 3 p orbitals. Each of these can hold 2 electrons, so 2, 2, 2, 2, that gives you 8. If in addition to those you have d orbitals, then you can hold more than 8. The octet rule is only true strictly true for the elements in the second row of the periodic table, because those only have s and p orbitals. But sulfur has d orbitals, so it can hold more than 8 electrons around it. Well, here we have a nucleophilic oxygen, and these hydrogens are slightly positive and very vulnerable because the conjugate base of sulfuric acid is very stable. So the oxygen steals one of those hydrogens, and the hydrogen can only form one bond, so the bond it already has, those electrons go onto that oxygen. So there's our proton transfer. That oxygen now will have a positive charge, and that now is an amazing leaving group. If that pops off of the molecule, it's water, which is very stable. So now we can have loss of that amazing leaving group. So the leaving group takes its electrons and leaves the molecule. Becomes water. And the carbon that was sharing those electrons now is missing electrons, has a full positive charge. So there's our carbocation, intermediate. Now that carbocation intermediate is a tertiary carbocation. There's no more stable position next door, so as we saw before, we're not going to have carbocation rearrangement. The next step is nucleophilic attack. So here's where we need to look back and see what our nucleophile was. We saw that our nucleophile is MEOH, which is really just CH3OH. It's a methyl group on an alcohol, OH. So here, if you have CH3OH, that oxygen is slightly negative. The hydrogen and the carbon that it's bonded to are slightly positive. And so the oxygen is nucleophilic, and that's what attacks the electrophile. So there is our nucleophilic attack. So we have this structure now. The oxygen has a full positive charge. To get rid of that positive charge, we just have to do that last proton transfer. And so we can transfer that to several things, but I think that we have a couple things available. You could imagine, for example, having the conjugate base of the sulfuric acid swoop in. Anything with a negative charge or lone pairs could act as the base here. So this oxygen with a full negative charge, that can take its hydrogen back, and those electrons in this bond can go onto the oxygen to stabilize the positive charge there, so that what we're left with is the molecule we wanted. So they're going to write that CH3 as an Me, as a methyl group, but it's really the same molecule. And so this whole thing is the mechanism for that change. First you have a proton transfer, loss of a leaving group, nucleophilic attack, and another proton transfer. All right, let's try it with F. So in the case of F, the first thing you want to do is to look at the leaving group and see whether it's a good or bad leaving group, because we want to see which of these steps are going to be included in our mechanism. Well, our leaving group is OH. OH is a terrible leaving group, as we saw in the last example, because it's not stable with a negative charge. So we have a bad leaving group, and we need to make it a good leaving group, so we'll have to do this proton transfer. You always do loss of a leaving group. Here, if you think about carbocation rearrangement, imagine what the molecule would look like if the leaving group were replaced with a positive charge. So that carbocation is secondary, because this carbon is bonded to two other carbons. Next door, there are so many carbons there. If you were to have a methyl shift, then that position, that would give you a tertiary carbocation. That's a more stable carbocation. And so this carbocation will rearrange. We will have to consider carbocation rearrangement. We always have nucleophilic attack, and then if you look at the nucleophile, the thing that we added could be coming from MEOH. So even though there's an H2SO4 there, we have an MEOH, so that's our nucleophile, because that's what's added onto the molecule. That does not have a charge. Remember, the Me is CH3, it's a methyl group. So there's no full negative charge there, and if there's no full negative charge, then we have to do a proton transfer to get rid of the charge that develops when after that nucleophile attacks. So this is about the most complicated mechanism you could have for an SN1. We're going to have every single one of these 5 possible steps. All right, well, let's get to it. And first, we'll just add some room. Okay. All right, well, we have our original molecule. And the first thing we need to do is this proton transfer. Now, we have a strong acid, sulfuric acid, and so that is going to donate one of its hydrogens. Remember, sulfuric acid, you have the 2 double bonds to oxygen, and then single bonds to oxygen, and then hydrogen. Those hydrogens are slightly positive, and they're also really vulnerable, because the conjugate base here is very stable, stabilized through resonance. The allylic, that lone pair will be allylic to 2 pi bonds. And this oxygen is slightly negative, and the carbon is slightly positive, hydrogen slightly positive. There's a whole bunch of charge we could see here, but in order to get the proton transfer to turn the leaving group into a better leaving group, we take the lone pair electrons on that oxygen, and those steal one of those vulnerable acidic hydrogens in sulfuric acid. The electrons in the bond already to the hydrogen go to the most electronegative place nearby. That's going to be the oxygen. So that's our proton transfer step. And that turns this OH into, into an H2O. And it has a full positive charge. And we also have the conjugate base of sulfuric acid, so we have that. But what we have now is an awesome leaving group. And so we can go on to that second step, loss of a leaving group. So the leaving group is going to take its electrons and pop off of the molecule. So that will leave us with those two structures. We've got our water, came off the molecule. And then where the leaving group left, we have a carbocation. This carbon had these extra electrons there, they left, and they became a lone pair on the water. And so you have that carbocation there. Now we did say that we have a carbocation rearrangement here. And the reason for the carbocation rearrangement is that this carbon is only secondary. It's bonded to two other carbons, so it's secondary. But next door, you could have a methyl shift. One of these methyl groups can move with their electrons over. That's your carbocation rearrangement. And so now you only have one methyl group left there. The other methyl group has gone to the other carbon. And now the carbocation here is on this other carbon, and that is tertiary. It's bonded to 3 carbons. So that's more stable because it's able to borrow negative charge. It's able to borrow electrons from more carbons. So we have our carbocation rearrangement there. Then we're going to have nucleophilic attack. So our nucleophile was this MEOH, methanol. I'm going to write it as CH3OH. The oxygen is slightly negative. The hydrogen and the carbon are slightly positive. Note that the oxygen here is really bonded to the carbon, not to those hydrogens. The hydrogens are also bonded to the carbon. So it's the carbon that's slightly positive. It's losing its electrons to the oxygen. And so the lone pairs on that oxygen are going to act like nucleophiles, and they'll attack that carbocation. So there's our nucleophilic attack. And so we have the methanol added, but it has a full positive charge. So to take care of that positive charge, we just have to do that last step, the proton transfer. So in this case, we can take anything that has a negative charge or a lone pair. We could use water. We could use the conjugate base of sulfuric acid. We could even use a methanol molecule that's in there. Anything that has a lone pair or a negative charge can come in and take this hydrogen. And those electrons will go onto the oxygen and help to stabilize the positive charge there. So that's our last proton transfer. And what we end up getting here is the exact molecule that we had wanted. Now, the exercise is going to have an Me there, standing for methyl, but that's the same thing as a CH3. So our final product is that. That's exactly what we had anticipated, what we were hoping for. And so this mechanism happened. This was the most complicated SN1 mechanism you could possibly have. You have every possible step. We had a proton transfer to begin with, and then we had loss of a leaving group. We had a carbocation rearrangement, we had nucleophilic attack, and we had another proton transfer. So to avoid making these videos too long, I'm going to continue this exercise in another video for now, and so we'll continue with